Okay, so now we're dealing with constant acceleration equations. And so I am showing you the table that literally lists these 5 equations. And now I'm going to start doing some problems. This equation sheet is also in your presentations folder on the website. So you can download it if you'd like. So, we have velocities, accelerations, and times. The only thing I'll tell you is that a lot of times we use d instead of x. I think this distance just helps the students better than x, so I might be replacing the x's with d's in the problems. And so now let's bring up my document camera. I'm just going to modify the screen a little bit. All right, well, you can see me. I don't know why I can't modify it, but anyways. So here's one problem. How long does it take a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at a constant 2.00 meters per second squared? So first you got to do your problem solving. I'm going to draw a picture. You definitely need to do these steps or I think you'll be lost very quickly. And it's going to go across a 30-meter intersection. And so that would be my D. And it says how long. So how long. They're looking for some sort of time. And then we just recognize the 30 meters. And so then if the car accelerates from rest is a big deal. So we have from rest. So that means D0 is 0 and V0 is 0. Okay? And you have a constant acceleration, and we know that A is 2 meters per second squared. So we drew our diagram, we listed all our knowns, and so what we want to know is the time, and what we have is a D, a total D, because if we start from 0 here, then this is 30 meters. So D final is 30 meters. So we have to look for an equation that uses T, A, and D in it from our equations. And so if you look at the equations, I'm going to move my... So if we go back to our equations, which one of those has x? Well, x's and d's. So you have, let's see, anything that has an x is a d. So this one has d's and v's and t's. Well, then we can't use that one. This one also is v's, a's, and t's. We don't have any. We have v0. That's it. So we're looking for time. So the other one that we have that has distances is these have x's, you have time, and you have acceleration. And then the last one is you have a final velocity, a's, and distances. But we wouldn't want to use this one because there's no time in this equation. So the only equation that you could find is this one. And you do have to go through this thinking process that I'm just talking to you about. So for this problem, you want to really make sure you have your knowns and what you're trying to find. So basically, it comes out to be, if I used that equation, so I would write, if you write them in D's, I can write the x's first. So it would be x0 plus v0t plus 1/2 at squared. Okay, so now I'm going to write them as d's, d0 plus v0t plus 1/2 at squared. So eventually I have to get to this t. I'm going to give you the long drawn out version. So first, d0 is 0. So this goes to 0, so we get rid of that. v0 is 0. So 0 times something is 0. So this comes. So the equation becomes d equals 1/2 at squared. Much more manageable. And now I'm going to rearrange the equation so I get t equals, because I have my final d and I have my acceleration. So first thing I got to get rid of is this 1/2. So if I'm dividing by 2, I'm going to multiply by 2. And so then this gets rid of this 2. So I have 2d equals at squared. I want t to be all by itself. It's being multiplied by a, so I'm going to be dividing by a. And so it would be t squared, and you have 2d over the a. The square, you want t by itself, so this has to be square rooted. When I square root that side, I have to square root the whole side. And so then we're eventually left with t equals the square root of 2 times the total distance over the acceleration. So you want to make sure this is an equation we're going to use a lot, and we're going to use it a lot in this format. So if I work over here, if I start to do my plugins, so t is equal to the square root of 2 times the 30, and I'm checking my units. I have it in meters, so that's awesome. And then the whole thing's divided by 2 meters per second squared. And so t becomes 2 times 30 divided by 2 equals, and then the square root is, on my calculators right here. So it's 5.477 seconds. Now you might want to keep going through these types of problems. So it took the car 5.44 seconds to cross the 30-meter intersection when it was going at a accelerated rate of 2 meters per second squared. Okay, so that's one problem in one scenario. I'm going to pick out a few more. I want to make sure I give us an example of some of the problems from some of the other equations. Okay, so for the next problem, you're designing an airport for small planes. One plane needs to reach 27.8 meters per second before taking off and can accelerate at 2 meters per second squared. If the runway is 150 meters long, can the plane take off? And then the second part of the equation problem is, what would the minimum length of the runway be? So the first thing you want to do is draw your picture. That's my lovely picture. And then you want to start listing your knowns. So the plane basically starts from rest. So that means V0 is 0 and D0 is 0, right? And then the final length of this, which is D, is 150 meters. And it says we have a constant. It usually says constant in there. Constant acceleration, so A is always going to be 2 meters per second squared. Okay, so then if I look at the equations again, so I have velocities, distances, and accelerations. So this one's velocities, acceleration, time. That's not going to work. This is all just velocities. This is distance, velocities, and time. I don't have time in my problems, so that still won't work. This is distance, velocities, time again, and acceleration, so this won't work. So out of process of elimination, the velocity squared is equal to V0 squared plus 2a times the total distance. That is the equation, because I have distances, accelerations, and velocities. So that's the equation you would want to use for this problem. So if I look at that equation, we have v squared is equal to v0 squared plus 2 times a times basically our d minus d0. Remember back when we did velocity, that would also be considered the delta t, a delta d. Okay, so we have v0, that goes to 0 because it's 0. So we're left with, sorry, this is a square. So we're left with v squared is equal to 2a times delta d. And we do have our distance. We have 0 and 150, so I'll do it that way. So then v squared is equal to 2a times delta d. So you have 2 times 2 meters per second squared. Always check the units, and they're working. And so then if I did d minus d0, this would be 150 meters minus 0, or 150. That's, though, pay attention, that's v squared. So eventually you have to square root the problem. So I'm just going to do this step. So you'd have 2, well, you can't see my cut. Okay, so you do 2 times 2 times 150, 600. So v squared is 600. And this turns out to be that it becomes a meter per second. So right now this is a meter squared and a second squared, but now I have this square root. So I have to, square. So I have to square root both sides. So v would equal the square root of all of that, which is the 600. So the square root of 600 is 24.494 meters per second. So for a plane to take off a 150 meter runway, they need to have a speed of 24.494. And we said our velocity was, it needed to reach 27.8 to lift the plane off the ground. So when it was so basically this is not going to work. The problem works, but this velocity needed to be over the 27.8. So that means, what would be the minimum length of this runway, given that you had to get up to the speed of 27.8? So we just use similar equation, same equation, but now we just list our knowns differently. So now we're looking for the total d. D is question mark. The acceleration is still 2 meters per second squared. This is my problem B. And now we have v0 is from rest, so that's still that. d0 is still resting. And then you have, now our final velocity has got to be 27.8 meters per second. So we're going to look for the delta d. So if we go back to the same equation, we'd have v squared is equal to v0 squared plus 2a, and I'm just going to call it delta d for now. So this goes to 0. So we have v squared is equal to 2a delta d, and now I have to do some rearranging. I want delta d all by itself, so it's being multiplied by a, and it's being multiplied by the 2, so I do the opposite. I'm going to divide by 2, and I'm going to divide by a. Whatever I do to this side, I got to do to this side. So now I have delta d is equal to v final squared divided by 2a. And so you're going to have 27.8 meters per second squared divided by 2 times the 2 meters per second squared. Still see that? And I got to hurry up and do this. So I got 27.8. I'm going to square it, and then I'm going to divide by 2, and I'm going to divide by another 2. So I'm getting the delta D is 190.